Next time you settle into a window seat for a flight, take a close look at the glass next to you. That familiar, rounded shape serves a critical mechanical purpose, keeping the plane from breaking apart. In the 1950s, commercial air travel was rapidly expanding. Passengers were flying higher and faster, enjoying pressurized cabins that felt like luxury lounges. At the height of this progress, a series of advanced airliners began tearing apart in the middle of the sky. Entire sections of the fuselage ripped away at cruising altitude. By the time the wreckage hit the ground, the planes were totally destroyed, leaving investigators to sift through fields of twisted metal. These inexplicable disasters revealed that engineers had critically misunderstood the environment of the upper atmosphere. Investigators spent months looking for standard failures. They checked the engines for mechanical trouble, reviewed the flight logs for pilot error, and mapped out the weather to see if severe turbulence played a role. But the evidence didn't match those causes. Investigators eventually identified the cause along the exterior of the cabin. These high-altitude aircraft were built with perfectly square passenger windows. For centuries, architects had built homes and office buildings using square and rectangular grids. Aeronautical engineers simply adopted this terrestrial design language and applied it to the fuselage. A sharp 90-degree corner works perfectly on a brick building resting at sea level, but when that same geometry is dragged up to 30,000 feet, the physical forces acting on the structure change. Applying a grounded design to the unique physical laws of the upper atmosphere proved to be a deadly oversight. At cruising altitude, the outside air is too thin for humans to breathe. To keep passengers alive, the airplane continuously pumps dense, warm air into the cabin. As this cross-section shows, a heavy artificial atmosphere is created inside the plane. That dense air constantly pushes outward against the thin walls. The higher it climbs, the stronger the pressure gets, inflating the cabin into a heavily stressed balloon. Every time the plane takes off, the metal hull expands to hold that pressure, and every time it lands, the metal shrinks back down. This makes the modern airliner a pressure vessel, fighting a continuous invisible battle to keep from bursting open. When a square hole is cut into the side of that expanding metal hull, it interrupts the natural flow of all that outward force. As this diagram illustrates, the pressure pushing through the metal skin must navigate around the window. When the force hits a sharp 90-degree corner, it gets trapped. The pressure builds and amplifies in those 4 precise spots, a phenomenon known as stress concentration. The consequence is visible in this fractured aircraft metal. Intense stress at sharp corners caused tiny cracks to splinter. Over dozens of flights, expanding and contracting caused severe metal fatigue. The cracks crept outward until the structure collapsed. In a pressurized environment, a 90-degree angle acts like a wedge, slowly driving the plane apart. To stop planes from falling out of the sky, engineers had to rethink the structural layout of the hull. They needed to eliminate every sharp corner. By replacing squares with circles, the outward pressure no longer gets trapped. As seen here, the force glides smoothly along the curve, diffusing the stress. Without those tight pooling points, the metal expands and contracts safely without developing stress fractures. This mathematical adjustment to the geometry of the fuselage solved the crisis immediately, becoming the mandatory standard for every commercial manufacturer across the globe. Aviation safety reached a new plateau when engineers aligned the aircraft's geometry with the physical laws of the upper atmosphere. Today, thousands of commercial jets soar safely through the upper atmosphere without structural failure. The routine safety of a modern flight relies on the lessons learned from those early engineering disasters. That curved glass is an active mechanical component, continuously routing thousands of pounds of pressure safely around your seat. When traveling at 600 miles per hour in a highly pressurized environment, every curve and shape serves a strict mechanical purpose. So the next time you lean against an airplane window, remember that you are looking through the exact shape that holds the entire plane together.